December 31st, 1862, 16 miles southeast of Cape Hatteras. The Atlantic Ocean is executing a violent physics test on the United States ship Monitor. This vessel is not a standard warship. It is a radical experiment in buoyancy and armor, an iron raft with less than 18 inches of freeboard designed for sheltered coastal waters and harbor defense. It was never built to survive the open ocean. Now it is being towed by the side-wheel steamer Rhode Island through a winter gale. The physics of the towing operation are failing. The tow hawser is under extreme tension, jerking the iron hull through the wave troughs. But the real crisis is not the towing cable. The crisis is inside the engine room, where a catastrophic chain reaction has already begun. The destruction of the Monitor is not caused by an enemy shell or a reef. It is caused by the failure of a primitive seal against modern hydrostatic pressure. The ship is famous for its revolving gun turret, a 120-ton cylinder of iron that granted the Union Navy superior firing arcs. But this rotation required a mechanical clearance. The turret does not sit flush with the deck. It rests on a brass ring with a small gap to allow movement. To keep the ocean out, the engineers relied on oakum. This is the only full explanation of oakum sealing you will hear. Oakum is a fibrous material made from old hemp rope treated with pine tar. Shipwrights hammer it into the seams of wooden hulls. When the hemp absorbs water, it expands, creating a watertight plug. It is a static solution for a static problem. But the turret of the Monitor is a dynamic load. As the flat-bottomed hull slams onto the wave crests, the entire ship shudders. The turret rocks on its spindle. This motion breaks the friction holding the packing in place. The seawater, driven by the immense weight of the Atlantic, acts like a high-pressure water jet. It blasts the oakum out of the gap. The seal vanishes. Water cascades into the ship directly under the turret. It runs down the bulkheads and finds the lowest point, the boiler room. The loss mechanics here are thermodynamical. The Monitor relies on steam pumps to expel water. These centrifugal pumps are powerful, but they are slaves to the boiler pressure. The water from the leaking turret does not drown the sailors immediately. It attacks the fuel. The incoming spray soaks the coal supply and hits the furnace fires. Wet coal burns inefficiently. The heat output drops. Without heat, you cannot make steam. Without steam, you cannot drive the pistons. The numbers on the pressure gauges dictate the survival of the crew. At full operational capacity, the main boilers maintain 80 pounds per square inch of pressure. This provides the torque to spin the large centrifugal pumps and eject the floodwater. But as the wet coal smothers the fires, the needle begins to fall. It drops past 60, then 40. The chief engineer reports the pressure has collapsed to 20 pounds per square inch. At this pressure, the pumps are merely churning water they cannot lift. The outcome is mathematically certain. The rate of flooding now exceeds the rate of expulsion. The tow line is cut to save the Rhode Island from being dragged down with the dying Ironclad. The Monitor loses headway and falls into the trough of the waves. Gravity takes over. The stern grows heavy as the water rises in the aft compartments. The iron raft inclines, lifting its bow toward the sky. Then it slips beneath the surface. As the ship descends, it initiates a final, violent rotation. The trapped air in the hull destabilizes the descent, causing the vessel to capsize. It flips upside down. The heavy iron turret, held in place only by gravity and a central spindle, slides out of its housing. The hull continues its plunge, inverted, heading for the bottom. It will not stop until it hits the seabed 240 feet down, where the physics of salvage will wait for a century. 240 feet. In the geometry of ocean salvage, this depth represents a precise mathematical trap. It is too deep for standard compressed air diving, where nitrogen narcosis turns rational engineers into confused liabilities. Yet it is shallow enough to be swept by the powerful boundary currents of the Gulf Stream. For over a century, the resting place of the Monitor remained a set of coordinates defined only by uncertainty. The ocean floor south of Cape Hatteras is a graveyard of shifting sands and magnetic anomalies that cloak iron wrecks from detection. The Atlantic does not surrender coordinates easily. In August 1973, a team from Duke University aboard the research vessel Eastward broke the silence. They were not looking for gold. They were hunting for a specific magnetic signature. Using side-scan sonar, they identified a target that defied the natural geology of the seabed. The acoustic return showed a flat, artificial shape. It was not a chaotic debris field. It was a coherent structure. But the data revealed a cruel twist in the physics of the wreck. The vessel had not landed upright. The Monitor had capsized during its descent, confirming the final moments of its surface life. It lay inverted, the flat armor belt of the hull pressing down into the sediment. The famous turret was nowhere to be seen on the sonar. It was pinned beneath the hull, crushed under the weight of the iron raft it once supported. The confirmation of identity required a human touch. But sending a human to 240 feet to perform heavy labor requires a radical physiological commitment. This brings us to the concept of saturation diving. This is the only time we will detail the mechanics of living at pressure. Standard scuba diving is limited by the clock. As a diver breathes compressed gas at depth, inert nitrogen dissolves into the bloodstream. If they stay too long or ascend too fast, that gas expands into bubbles, causing decompression sickness. This creates a hard limit on bottom time. A diver might spend 10 minutes working and 2 hours decompressing. This ratio is inefficient for heavy salvage. Saturation diving solves this efficiency equation by surrendering to the pressure. The divers do not return to surface pressure after their shift. Instead, they live in a pressurized deck chamber on the salvage barge, breathing a mixture of helium and oxygen. Their bodies are allowed to reach full saturation, where the tissues have absorbed the maximum amount of inert gas possible at that depth. Once saturated, the penalty is paid up front. Whether they stay down for 1 hour or 1 month, the decompression time required at the end of the mission remains the same. It takes days to bring them back to surface pressure. For the duration of the project, the divers are effectively extraterrestrials, living in a habitat where the atmosphere is roughly 8 atmospheres of pressure. In 1977, this capability allowed divers to recover the first major artifact from the site. It was not a gun or a piece of armor, it was a signal lantern, specifically a brass lantern with a red glass lens. The logic of this recovery was forensic. The historical record stated that a red lantern was hung from the turret as a distress signal during the sinking. Finding this specific object confirmed the timeline of the loss. It proved that the crew had followed protocol even as the pumps failed. The discovery led to a new legal classification. In 1975, the wreck site was designated as the first National Marine Sanctuary. This changed the rules of engagement. The Monitor was no longer just a shipwreck. It was a federally protected archaeological zone, but the ocean chemistry did not respect federal law. The salt water was eating the iron. The hull was collapsing. The urgency shifted from discovery to rescue. To save the ship, the engineers would have to dismantle it underwater, piece by heavy piece. The first target was the machine that had failed them in 1862. The engine. Removing a 24-ton steam propulsion engine from a shipwreck is not a standard lifting operation. It is a logical paradox. The engine is the structural heart of the vessel, bolted to the keel and encased in iron plating. When that vessel is lying upside down, 240 feet deep, the heart is effectively buried inside a collapsed rib cage. To extract it without destroying the rest of the ship requires a technique that is less like salvage and more like surgical demolition. In the summer of 2001, the mission objective was the primary propulsion unit. This was not a conventional reciprocating engine. It was a masterpiece of Victorian geometry known as the vibrating side lever engine. John Ericsson designed it with a specific battlefield constraint. A standard vertical steam engine would stand too tall, extending above the waterline where enemy shot could destroy it. Ericsson laid the cylinders flat on the floor. Instead of pistons pumping up and down, they drove heavy levers that rocked back and forth horizontally like the motion of a metronome. This kept the entire mechanism safely below the water level. Now that same low-profile design made it incredibly difficult to access. The engine was trapped behind the inverted hull plates. The divers faced a material problem. How do you cut through thick wrought iron underwater? Standard oxyacetylene torches rely on a gaseous flame, which is unstable at 7 atmospheres of depth. The solution involved 2 distinct cutting technologies. This is the only detailed breakdown of underwater cutting you will hear. The first tool is the exothermic cutting rod, often called a carry cable. This is a hollow steel tube filled with alloy wires. When oxygen is pumped through the tube and an electrical arc strikes the tip, the rod burns at over 10,000 degrees Fahrenheit. It does not just cut metal, it liquefies it. It can slice through iron, concrete, and marine growth instantly. But for more delicate work near the fragile artifacts, the team used hydroblasting. This system pressurizes water to 20,000 pounds per square inch. At this pressure, water ceases to be a liquid and becomes a solid blade. It shears through steel plates without generating heat or vibration. Working in saturation, the divers used these tools to slice away a section of the hull, exposing the engine room. They were not just cutting iron, they were dissecting a time capsule. The engine was heavily encrusted with concretion, a concrete-like layer of corrosion products and sea life. The team had to rig the 30-ton mass while it was still inside the wreck. They looped heavy slings around the main components, transferring the load from the rotting ship to a steel recovery frame. On July 16th, the lifting wires took the strain. The vibration side lever engine, which had not moved since the boiler pressure failed in 1862, broke free from the suction of the sediment. It rose through the water column, a dripping mass of black iron and green corrosion. As it broke the surface, it was immediately doused with fresh water to prevent the oxygen in the air from accelerating the rust. The heart of the Monitor was safe, but the engine was only the prelude. The true prize, the revolving turret, was still on the bottom, and unlike the engine, the turret was not just buried inside the hull, it was being crushed by it. To save the guns, the engineers would have to lift the ship off the turret, 8 inches. That is the combined thickness of the laminated iron plates protecting the gun turret of the Monitor. In 1862, this armor was proof against the heaviest Confederate artillery. But in 2002, it is facing a force that iron cannot resist, the weight of the ship itself. When the vessel capsized, the hull came to rest diagonally across the turret. The armor belt, a heavy strip of iron running the length of the ship, is pinning the cylinder into the sediment. This creates a structural deadlock. You cannot simply yank the turret out. If you apply vertical tension, the friction against the hull will tear the disintegrating wreck apart. To free the guns, the engineers must remove the armor belt. But if they cut away the belt, the hull it supports will collapse onto the divers. The solution requires changing the load path of the wreck. This introduces the concept of structural shoring. On a land-based construction site, you would use steel beams or hydraulic jacks to prop up a sagging wall. At 240 feet, in a high-current environment, rigid steel is difficult to deploy. The salvage team turned to a fluid solution. They utilized grout bags. These are large industrial fabric containers positioned underneath the overhanging sections of the hull. Once the divers place the empty bags, they pump a specialized cement mixture into them from the surface. The liquid grout fills the bag, taking the exact shape of the seabed and the jagged iron hull above it. As the cement cures, it hardens into a solid concrete pillar. This transfers the weight of the wreck from the armor belt to the seabed. The grout bags act as artificial bedrock. The divers installed these pillars systematically, creating a new foundation for the dying ship. This process mimics the stability that the oakum seal once provided, but instead of keeping water out, the grout keeps the iron from falling down. The callback to the original seal failure is ironic. The ship was lost because a seal failed, and now it is being saved because a new seal is being created with concrete. With the hull legally stabilized, the cutting teams returned to the workface. They used the exothermic rods to slice through the armor belt that was pinning the turret. This was heavy, dangerous work. The section of belt they needed to remove weighed thousands of pounds. When the final cut was made, the iron slab was lifted away, leaving the hull suspended on its new concrete pillars. For the first time since the sinking, the turret was visible. It stood alone on the ocean floor, a rusty drum measuring 20 feet in diameter. But the removal of the hull revealed a new, more terrifying constraint. The turret is not a closed container. It is an open cylinder. It has a roof, but it has no floor. The original wood planking that once served as the deck inside the turret has long since rotted away. The cannons are not bolted to the walls, they are resting on carriages that sit on the sediment. If the engineers lower a claw and lift the turret by the rim, gravity will empty the contents. The 2 Dahlgren guns, the heavy iron carriages, the coal, and any human remains will fall out the bottom and be lost in the silt cloud. The friction of the mud is the only thing currently holding the interior together. They need to lift a 120-ton cylinder without spilling a single ounce of sediment. The physics of the lift have shifted from heavy salvage to a delicate balancing act. They need a way to build a floor under the turret before it leaves the bottom. This requires a mechanical assembly so complex it effectively builds a cage around the artifact while it is still underwater. 41 days. That was the rigid time constraint imposed on the 2002 recovery mission. The Atlantic hurricane season does not negotiate with salvage schedules, and the window for safe operations was closing. The divers and engineers had stabilized the hull and exposed the target, but they still faced the physics of the lift. They had to raise a disintegrating iron cylinder containing unknown tons of mud and artifacts without a bottom to hold it all together. To solve this, the Navy engineers designed a specific piece of machinery known as the spider. This was not a standard crane hook. It was a massive steel claw with 8 hydraulic legs, custom-built to match the 20-foot diameter of the turret. The plan required a sequence of movements so precise it resembled a mechanical ballet performed in slow motion at the bottom of the sea. The operation followed a strict 3-step geometry often referred to by the salvage team as the artifact Oreo. First, the spider was lowered over the turret. Its 8 legs descended around the outer rim, locking onto the iron armor. Once the grip was secure, the crane operator on the surface barge applied just enough tension to lift the turret a few feet off the seabed. This was the moment of maximum risk. The turret was now hanging by friction, its contents held in only by the cohesion of the mud. Second, a heavy steel platform was lowered to the sea floor next to the suspended turret. Divers worked in the shadows of the suspended load to guide the platform directly underneath the floating cylinder. Third, the spider was lowered until the turret rested on the platform. The divers then bolted the legs of the spider to the platform itself. The turret was now the filling in a steel sandwich. It was fully enclosed. The bottomless bucket finally had a floor. Now the team faced the most dangerous phase of any offshore lift, the transition through the splash zone. This brings us to the concept of dynamic loading. When an object is submerged, Archimedes' principle provides an upward buoyant force that counters gravity. The water supports the mass. But as the crane pulls the object through the surface, that support vanishes instantly. The effective weight of the load spikes. But dynamic loading is more than just the loss of buoyancy. It is the interaction between the wave energy and the lifting cable. If the salvage barge heaves upward on a wave crest while the load is still submerged, the drag of the water resists the motion. This adds effective mass to the lift. A 200-ton static load can suddenly exert 300 tons of force on the wire. The cable acts like a giant spring, storing and releasing energy. If the period of the wave matches the natural frequency of the cable, the load can begin to bounce violently, snapping the wire or crushing the crane boom. On August 5th, the winch engine on the derrick barge Wotan began to spool. The cable tightened. The numbers on the load cell climbed. The gross lift weight, including the spider, the platform, the turret, and the wet silt, hit 235 tons. The assembly rose through the water column, protected from the dynamic forces by the sheer lifting power of the heavy lift crane. It breached the surface, water cascading from the gaps in the armor. For the first time in 140 years, the turret of the Monitor felt the air. The lift was secure, the sandwich held. But as the water drained away, the preservation clock started ticking. The iron was safe, but the mystery of what lay inside the mud was about to be revealed. The recovery of the turret was not the conclusion of the salvage operation. It was merely the transfer of the problem from the discipline of physics to the discipline of chemistry. When an iron object spends 140 years submerged in salt water, it undergoes a fundamental molecular change. The metal becomes porous. It absorbs chlorides from the ocean. While the artifact is underwater, these chlorides are stable. But the moment the iron is exposed to the atmosphere, a violent reaction begins. The salt crystals expand, cracking the metal structure from the inside out. If the Monitor turret had been left on the dock to dry, it would have disintegrated into a pile of rust within a few years. To prevent this destruction, the turret was immediately submerged in a 90,000-gallon tank at the Mariners Museum in Virginia. Here, the process of electrolysis began. This is the final technical concept we must define. Electrolysis is the reversal of corrosion using direct current electricity. The engineers placed the iron object in a solution of water and sodium carbonate. They introduce a mild electrical charge, making the artifact the negative cathode. This electrical pressure forces the negatively charged chloride ions to migrate out of the metal and into the solution. It is a slow molecular extraction. The process cannot be rushed. Desalinating the 120 tons of wrought iron in the turret will take decades of continuous current. Inside this chemical bath, the archaeologists began the excavation of the mud that had been trapped by the spider and the platform. This was forensic work performed by hand, removing the silt ounce by ounce. As they lowered the sediment level inside the cylinder, the operational reality of 1862 emerged. They found the twin 11-inch Dahlgren guns still mounted on their carriages. The guns were fully loaded, ready to fire, with the rammers stowed in position. The crew had fought their station until the steam pressure died. But the sediment held more than just ordnance. Near the breech of the guns, the excavators discovered the remains of 2 crew members. This discovery answers the open loop of the sinking mechanics. When the ship inverted and the turret dislodged, these men were trapped inside the iron drum. They rode the turret down to the sea floor. One wore a gold ring, the other had a comb in his pocket. Their presence transformed the turret from a machine into a tomb. The identification of these men required a new level of forensic science, comparing DNA from the bone samples with living descendants. It was a salvage of identity that took as long as the conservation of the iron. The legacy of the USS Monitor is not defined by its brief career or its loss. It is defined by the engineering audacity required to bring it back. The salvage teams had to overcome the dynamic loading of the open ocean, the crushing pressure of the deep, and the chemical entropy of the iron itself. They used saturation diving to work beyond human limits. They used hydroblasting to cut without heat. They used grout to turn fluid into stone, and they used electricity to reverse time. The ship that changed naval warfare in 1862 changed marine salvage in 2002. The iron raft is no longer at the bottom of the Atlantic. It is safe, slowly releasing its salt, reminding us that with enough force and enough logic, even the ocean can be made to surrender its dead.